Internal Routing Protocols Part 2, Advanced EIGRP Configuration. As you can see from the objectives on the screen, the goal of this nugget is simple. It's to show you some configuration examples of, I would say, the advanced commands of EIGRP. EIGRP is, in my opinion, the most powerful protocol that's out there with some of the simplest configuration behind it. That's because Cisco invented it, and it is a very easy protocol to configure. So we're going to start off with what I call EIGRP coffee. Let's get our blood flowing, looking at the facts and beyond. Some of the facts that you may have known about EIGRP, but it'll act as a good review, and some of the facts that you may not have known. There's one that I'm going to show you that I did not discover until the last year, and it was one that ate away at my very being for the longest time. I'll explain it when we get there. We'll also talk about the EIGRP commands and configuration examples, and I kind of should have transposed those by saying EIGRP configuration examples to see the commands. We're going to get into some advanced redistribution, route filtering, pretty much all you can do with EIGRP. But before we get into all that configuration, let's hit the EIGRP coffee, get our blood flowing with EIGRP, some of the facts and not so well-known facts about EIGRP. First off, you'll never hear Cisco call it this, but EIGRP is technically a distance vector routing protocol. The closest thing you'll ever hear Cisco get to is advanced distance vector routing protocol, and they really do prefer to call it a hybrid routing protocol. And if you think about it, it is. It takes the easy configuration of distance vector and combines it with some of the link state factors like fast convergence time, very fast convergence time. It's one of the fastest to converge out there. Very low processing, low memory utilization, variable length subnet masking, and it can do manual summarization anywhere in the network. That's a huge benefit that even most of the link state routing protocols won't give you. But because it is technically a distance vector routing protocol, a lot of those distance vector loop prevention systems may be in place. Watch out for split horizon. I don't know how many times it's caught me on a frame relay or an ATM multi-point network when I'm setting everything up and using EIGRP, and I don't even think about it because in my mind, I don't even think about EIGRP as distance vector. It's just kind of an advanced routing protocol. And suddenly some of the routes aren't showing up where they should, and I start racking my brain, what's going on? And then I realize, oh yeah, on that router that has the multi-point interface, I need to disable split horizon or else those updates won't propagate. So watch out for that one. Second, this is a classless routing protocol. It does do auto summarization by default, so it behaves like a classful until you disable that. And it will find the best path through the network using the bandwidth and delay by default. Now, before we even get into the command of the day that I have down below here, I want to talk about bandwidth and delay. The reason why is for years I was confused. I thought bandwidth, well, that's what you statically configure under the interface, right? You type in bandwidth followed by what bandwidth that interface has, and that's what it uses, and that's true. But delay, I figured, was just dynamic. It would detect how long it takes a packet to get from one point to the others and say, well, that's your delay. That is actually not true. Delay is a static configuration. It's a static configuration under interface configuration mode, and it blew my mind when I found that out. I thought, well, that doesn't make sense. Why would you even have two static configurations to find the best way around the network? And the reason why is because, number one, delay is static because it keeps the memory and processor cycles very low on EIGRP. If you wanted a dynamic factor, which I'll talk about in a moment, that will definitely go way up. The second reason, the reason they have the delay is so that you don't have to lie to the router on the bandwidth. I mean, think of this. You have two T1 lines that are going to a single location, and you want EIGRP to prefer one over the other and not really use it for load balancing. How would you do it? Well, typically you would go in and you would lie to it. You would say, well, the bandwidth on this one is a T1, and the bandwidth on this one is maybe 500K, which is low enough that it's not going to load balance between those two unless you tell it to. Well, what you've done is you've tricked the router, and the problem is that you've not only tricked it for EIGRP, but you may have tricked it for a lot of the other functions that that router is doing. For instance, quality of service, QoS, constantly uses that bandwidth on an interface to figure out how to do queuing best
on the interface. And if you are lying to the router and telling it has less bandwidth, well, that's really going to affect your queuing and your quality of service. So instead, what you can do with EIGRP is set the bandwidths to be equal and then tweak the delay to choose one over the other. Okay, so you can have the delay being much higher on one because the delay is only used for EIGRP. It doesn't really factor in into any of the other functions of your router. Now this one is the command of the day, and the reason why is hours and hours of looking. I never found this command on Cisco's website. You know that bandwidth and delay are used to calculate the metric by default, right? But EIGRP can use three other factors. They are the load of the line, the reliability of the line, and the maximum transmission unit. However, on Cisco's website, it's very difficult, next to impossible, to figure out how to turn those factors on. The reason why is because Cisco highly recommends that you do not use them. Even though they are available to you, even though you can factor in, for instance, the load of the line. They say don't do it because your processor utilization and your memory utilization for EIGRP will go way up, and it can constantly cause recalculations of the routing table. In most of the documentation, matter of fact, all the documentation I found on their website, they always said, if you want to turn these on, contact Cisco TAC and they'll tell you how to do it. Well, you don't need to contact Cisco TAC. Here's how you do it. If you want to enable those, under router configuration mode for EIGRP, you type in metric weights followed by a type of service, and this is always, always 0. It lets you type in 1 through 8, but even the context-sensitive help, it will tell you this is always 0 because Cisco hasn't really begun utilizing that yet. Then you have the K values, K1, K2, K3, and you may have heard of these K values before because these actually match up to each one of those metrics. They factor into a huge mathematical formula that EIGRP uses to calculate the best path. And I'm not going to put that all on the board right here. It's needless information. What you do need to know is that K1 is bandwidth, and that's set to 1. K3 is delay, and that's set to 1. All of the rest of these are set to 0. And in a mathematical formula, if something's set to 0, most likely it's not going to be factored into the calculation, and that's exactly how this works. But here's the note that I have matched these up for you. K2 matches up to the load. If you want to enable the load, go ahead and change this over to 1. K4 matches up to the reliability. K5 matches up to the maximum transmission unit. So you can change these to 1, and the cool thing is this metric weights command lets you adjust these from a value from 1 through something like 404,295,000,000 something. It goes on and on and on for a value that you can adjust these to. So what does that mean to you? Well, it means that you could maybe adjust the bandwidth and delay way up and have the reliability, which is K4, play a factor in it, but not that much of a factor. You can maybe adjust it to 2 or 3, while this is 50 or 60. So this is all in that mathematical formula, which Cisco does have on their website if you want to check that out. But that is how you can adjust your K value, something I've been trying to find for years. Finally, EIGRP's dual algorithm is the only routing algorithm that keeps a feasible successor route. First off, dual stands for diffused update algorithm. What is it? A marketing term, in my opinion. It's something Cisco calls EIGRP's algorithm that's a little bit different than what every other link state routing protocol uses, which is the shortest path first, or SPF algorithm. Dual is the only algorithm that keeps a feasible successor, which is a fancy way of saying backup route. Here's the idea. Let's say you have a router, and this router has a connection up here that reaches a destination, and it's got a connection down here, and this is a T1, and this is maybe an ISDN 128K. So you don't want to load balance since the bandwidth on this is so much lower, but you do want this to be considered a backup route. If you are using the SPF algorithm, which is essentially every other routing protocol, ISIS, you have OSPF, all of them really use SPF. But if you're using that algorithm, this is not even considered. It says, I have that, it's in my topology table, but this goes in the routing table and no ifs, ands, or buts about it. Now what happens when that T1 line goes down? Well, if you're running the SPF algorithm, it has to run the algorithm itself again, which takes time, go through the entire topology and say, aha, I found a backup route. Not so with EIGRP's dual. It will keep a successor, which is the primary, and a feasible successor, which is a backup in its back pocket at all times. And there are some considerations for this, but most of the time it will keep a backup route. So when that T1 line goes down, snap, it fails over. It's on the ISDN connection. No SPF algorithm running, figuring out, grinding up that topology table. It instantly knows that it has a backup route. Now that it's using that, it will start looking for another backup route. It'll run the algorithm in the background and start saying, okay, well, do I have another feasible successor now to this one in case this one fails as well? So it has a much faster convergence time than a lot of the other link state routing protocols out there, and that's what makes it such a powerful protocol. Its only drawback, the fact that it is Cisco proprietary. Only Cisco routers can run this protocol, and that is its biggest drawback. However, since we're talking the CCIE lab, do you think the chances are pretty good that you will get all Cisco equipment? I definitely do. So EIGRP is the winning routing protocol. And here's our topology that we're going to be setting up. It's getting pretty complex here. We have OSPF area 0 that is defined down here with these two routers that are in that area. Both of these routers are also connected to EIGRP Autonomous System 500. In the OSPF world, these are Autonomous System Boundary routers. In EIGRP, they're just routers that are going to do redistribution. Over here, we have a RIP version 2 network that router 4 is plugged into, and we'll redistribute into that. And router 1 is the hub router of this frame relay topology. Now you can see, just kind of take a step back and glance at this topology. Do you see any problems? Go ahead and, if you could, pause this nugget right now. See what problems that you can figure out based on just the fact that we are going to be redistributing on every router that's connected to another protocol. And also, just take a look at the frame relay topology. So go ahead and pause it right now. Okay. I hope you paused it. But here's some of the things that I see just looking at this topology. Number one, router 1. Hub router. What did I just tell you on the facts? Well, it's got a multi-point interface. Think split horizon. Over here, since we're going to be doing redistribution from both router 2 and router 5, I'm thinking potential router loop and routing loop, because EIGRP routes are going to be going into OSPF, over to router 5 from router 2, and then back into EIGRP, and vice versa. OSPF routes, this loopback interface, for instance, are going to be coming from router 5 to router 2 and be getting kind of looped both directions from router 5 and router 2 in the EIGRP autonomous system. So, definitely got some things to consider here. Now, to make it a little bit more efficient, I've set up EIGRP and RIP and OSPF on just about every router, including these ones down here. Router 1 is pretty much the only place I haven't done it, and it's going to be a very simple config for EIGRP initially. I'm just going to go into router EIGRP 500. First command I always type is no auto summary. Turn that off so this can become a full class less routing protocol. And in this case, I just want to enable EIGRP on all networks, so I'll type in network 170.100.0.0. Since that's a class B network and all the networks over here start with that, we're good to go. And at this point, we should be receiving the routes. Let me hit a Control Z and do a show IP route. And sure enough, in the list, we see the Ds, that's EIGRP 170.100.4.2 and .3. Let's look at our topology. There's 170.100.2, so there's our two networks right there. .3 and 170.100.4. See, I enabled EIGRP down here, but since it is a class full routing protocol by default, I didn't use any special wildcard mask because router 4 didn't have an iOS that supported it. So it's even advertising this RIP network as if it were an EIGRP route, because 170.100 encompasses both sides of that router. So we'll have to take a look at that as well. So let's go ahead and do a little bit of redistribution. As a matter of fact, let's even make this a little more interesting over here on the RIP side, because that's where I want to start off. And let's
let's go ahead and add some loopback interfaces. I'm going to add 155.155.0 through 5 to router 4, and poof, through the magic of video, it's already been done. I've added those interfaces and included them into the RIP process. So let's redistribute over on router 4. I'm going to do a show IP protocols first off on router 4, just so we can see what's going on. You know what? Before we even analyze that output, let's do a show IP interface brief. We see the Ethernet interface, which is in the RIP domain. We see the serial interface, which is in the EIGRP domain. That's this one coming out right here, Ethernet down here. And then we see all of those loopback interfaces, 0 through 5, that are all in the RIP domain as well. Now when we do a show IP protocols, we see that EIGRP is only routing for this 170.100 network. It's already been enabled. And its only routing source is router 1 that it's found. You also see, this is a great command, in here we see all those K values. Again, K1 is bandwidth, K3 is delay, and the other K values have been zeroed out, so they're not even affecting the metric whatsoever. Now as for RIP, we see that it is version 2 indeed. All of the interfaces that it's enabled for is version 2 as well, or are version 2. And we see which networks it's routing for down below. Now let's say we have a requirement. I make these scenarios a little more interesting as we go. Let's say the CCIE lab or the requirements say that we need to redistribute, but network, we'll say 155.155.3 cannot be advertised to the EIGRP domain. All the rest of them need to be advertised. That throws an interesting twist into this. Let's do it. First things first, I'm going to go into router configuration mode. And let's see, how can we filter out that 3 network? We could just do a redistribute RIP and that would send everything over, but how can we filter out that 3 network? Well, there's a couple ways that come to mind. First off, a distribute list would do it by filtering it from the EIGRP side. I could say distribute list. Let me just bring you back to the topology. Router 4 would have a distribute list on the outbound direction saying do not send 155.155.3 to router 1. But theoretically, it's in the EIGRP domain. That's something to watch out for. If it ever says do not let that network enter the EIGRP domain, yikes. By redistributing and then filtering right here, the network is in the EIGRP domain. You just have filtered it on the first router that it got to. So we have to find a little different method. How about this? How about the first thing that we do is define an access list that encompasses that network. We'll say access list 3 since it is the 155.155.3 network. And I'm going to say to deny 155.155.3.0 with a wildcard mask that matches that one exactly. And then we'll say access list 3 permit any. So now we've got those 2 statements in there. Now we can catch it during the redistribution process by doing a route map. And with my route maps, I always name them after the protocols that they're redistributing. So I'll say RIP to EIGRP. That's just the naming convention I've come to know and love. And the first thing that's going to come up here is we need to do a match statement. So I'll do match IP address, and it's going to ask us for an access list number. We did access list number 3. So I'll type in match IP address 3. Enter. So at that point, we are matching 155.155.3. We don't even need to do any set commands because the route map is that simple. We just want to deny. We match that access list that says deny the one network and permit the other one. Now let's get into the router configuration mode. Router EIGRP 500. And in here, the command I can use is redistribute RIP followed by a metric because I need to redistribute it into the EIGRP domain. We'll do 1500 kilobits per second for bandwidth. The delay is 0, 255, 1 for the load, and 1500 for the MTU. After you do that a few times, you won't even need to hit the question mark because you'll get that pattern down. From there, I'm going to reference the route map. So let me just make sure I've got everything here. As I redistribute RIP into EIGRP, I'm setting this metric, and I'm only going to redistribute the routes that match the route map RIP to
EIGRP. That is what I named it, correct? Correct. RIP2 EIGRP. See, even my own naming convention I forgot already. I hit enter, and voila, the redistribution should be happening. And let me go up now to router 1. Let me just jump up to router 1, clear the screen of all this gibberish, and we'll do a show IP route. So I type that in, and voila, let's see what we have here. External route 155.012, beauty. And 3 is missing because it was filtered out by that route map that we applied to the redistribution. So at this point, let's get back to our topology here. At this point, we now have RIP going into EIGRP. Now, we won't even bother redistributing EIGRP into RIP because there's no real RIP routers other than router 4, which has all the EIGRP information anyhow. Let's now turn our attention over here because it's going to get a wee bit more interesting. OSPF Area 0. Now our CCIE lab has dictated we must perform redistribution on router 2 and router 5 fully in both directions. So that means that we're going to have to apply some filtering there. I'm just kind of looking at that and going over it in my mind. What kind of filtering should we do? And challenge yourself as well. Pause the video. Think about it. What kind of filtering, if we are redistributing OSPF fully into EIGRP on router 2 and router 5, and vice versa on those two routers, EIGRP into OSPF, what kind of filtering do we need to do, and how would you do it to keep those from looping around the network? Wow. Hopefully you paused the video and you kind of took a look at this. If not, do that now, because I really want you to kind of work through this in your own mind on your own, because this is a tough one. I threw the gauntlet down, and I'm hesitant to step up to this challenge. Let's copy this section of the diagram, and I want to put this on a whiteboard on its own so we can talk through this together without getting all that other mishmash in the way. All right, we've got these two routers in the OSPF domain. We're going to have EIGRP routes coming down into the OSPF world, and if we don't filter them out, they're going to loop right back around and end up going back in, and that's going to be a killer route loop. We don't want this. So we'll have to put a filter in place. We'll have to have an OSPF filter, and filtering with OSPF is really easy to do. I know this isn't the OSPF nugget, but these technologies do kind of bleed together sometimes. So we're going to put a filter on here that says only when redistributing OSPF into EIGRP, which is this direction, only allow internal OSPF routes to get out. Don't, because you can actually say, don't let external routes go back out. That'll be how we can filter from OSPF into EIGRP. But now let's think about the other way around. That keeps EIGRP routes from getting into EIGRP once again, going through OSPF and back out again. But what about these routes inside of here, like this loopback 0 interface? We're going to redistribute that from router 5 and from router 2. So at that point, it's going to probably load balance between those. We're going to have one packet to router 5, one to router 2, since these are both set at a T1 speed. They're both the same speed. So here's how we can do this. We can take loopback 0. You following this here? We'll take loopback 0 and advertise it out, and also this one right here. We'll advertise them out, and we'll say router 5, when we do the redistribution, we'll say it has a better metric. So we'll just put a little up arrow. Better metric this way. And when we redistribute on router 2, we'll set a lower metric this way. That'll do it, because that'll go ahead and say this is the preferred route, at least for that network, and this is the not so preferred route. So since EIGRP is only load balancing between equal paths right now, it won't even consider this one unless this one's down. So we still keep our redundancy in place. Cool. All right, well, if you didn't follow all of that, we'll walk through it together on this live. Let me just get the right diagram up here. In this live demo, we'll go ahead and walk through each step of that I described. Let's start off down here on router 5 and orient ourselves as to what's going on there. I'm going to do router 5, and let's first off just do a show IP route. See what kind of routes we're receiving here. It looks like we're getting all those external routes from the RIP domain. They're being passed down here. We are getting, look at this. I'm seeing a few of the EIGRP networks. We see this one, which is 200, that is coming from this point-to-point interface. I see 10, which is coming from the Ethernet interface up here, and I see 4. Are you thinking of something that we forgot here? I think we forgot to turn off split horizon on router 1, because we should be seeing more. We should be seeing this guy, but since it's being received on serial 0.1 and sent out, split horizon's blocking it. So you know what? Before we even start the redistribution process, we need to fix that. We'll go on router 1, global config mode, interface serial 0/0.1. No IP split horizon EIGRP 500. So we're saying turn that feature off. And look at that. We destroyed all our neighbors because we changed the configuration completely now of EIGRP. And it's now going to receive and send those updates out on that same interface. So now if we hop down to router 5, I know these neighbors are still coming back up. But we should see a few more routes end up in that routing table as that neighbor relationship reforms and reforms with the split horizon. Matter of fact, let me pause this recording until we see those routes show up so I know I've got a full routing table before we begin with a redistribution. All right, well that didn't take too long. Let me scroll back up so you can see what happened when I paused the recording. I paused right up here, and as soon as I paused it, it showed the neighbor just went down because the peer restarted. I did a show IP route. No routes. Then the neighbor came back up. Then I did this final show IP route that you see the output right here. And now we're seeing the 3 network, which we didn't see before because split horizon was blocking it. Okay, so now we have full routing tables on every single router. So I'm sitting on router 5. Let me go ahead and get up into global config mode, and I'll go into router EIGRP 500. Because I want to redistribute OSPF into EIGRP first of all. And I'm going to do that by walking through this redistribution command step by step, because it's going to have some pretty intricate stuff in here. We're going to do redistribute OSPF1, do a question mark. The first thing that I want to do is I want to match certain OSPF routes. And the certain routes I want to match are only internal ones. Let me go back to the slide and make sure you see what's going on here. Router 2 is going to be doing this redistribution. It's going to have OSPF routes, or sorry, EIGRP routes coming into OSPF here. You see this? We're going to redistribute EIGRP into OSPF. They'll be tagged as external routes right here, so when router 5 gets them, it will have its internal OSPF routes, but it will also have those external routes from router 2. So you see what we're doing here? I'm saying on router 5, redistribute OSPF into EIGRP, but only match internal routes. Don't match those external routes or else we'll cause a loop. We'll have the EIGRP externals coming right back out to EIGRP. So I'm saying match internal. What's the next step? Metric. I'm going to set the metric, and this one I'm going to set to be very good. I want this one to be my preferred router when I redistribute OSPF because it has the attached loopback interface. Let me get the diagram. It has this one right here. I want router 1 to go through router 5 to get to that loopback rather than going through router 2. So I'm going to set the metric better on router 5. So those are the preferred routes. So I'll say 3,000 kilobits per second here. The delay will be 0, and that should pretty much do it. These aren't even factored into the calculation. They're just required for the redistribution. All right, let me make sure I've got everything here. We have the match statement, matching internal routes, the metric, it's a better metric. Route map, we could have done a route map and done the same thing inside of the route map, but why do that? We can do it right here. So at this point, we're now sending the OSPF routes up to router 1, and I'm going to do that down on router 2 as well. On router 2, I'll get into router EIGRP 500, and I'll do redistribute OSPF1 metric. First things first, I'm going to set it to a lower metric. Remember, 3,000 kilobits per second on router 5, 1,500 down here. The delay will be 0, 255, 1, 1,500. I won't use the context-sensitive help. But I do want to make sure I don't forget this. Otherwise, we'll have a loop in the other direction. I want to match only internal OSPF routes. I don't even want to mess with any of the not so stubby areas, NSSAs. We'll talk about all this stuff when we get into OSPF. But I'm only sending internal routes. into there. So at this point, what have we done? We've got router 5 and router 2 both sending OSPF routes up to router 1. Router 1, I'm going to verify it in just a second. Router 1 is going to prefer router 5 as the next hop because it has a better metric. And even though we haven't redistributed EIGRP into OSPF yet, we've already put a filter in place to block those EIGRP routes from getting back out because we're matching only internal routes on router 2 and router 5. Cool. This stuff gives me a buzz. I love it. Let me get up to router 1. Tell me this isn't cool. Let's do a show IP route. And, oh, look at this. We are redistributing, but we are load balancing on both of those. Huh. Load balancing. That's interesting. See, I'm milling this over in my mind right now. It looks like we're using both this neighbor, which is router 2 down here, R2, and this neighbor, which is R5, to get there because the metrics are equal. Let me think about that real quick. Well, I did a little troubleshooting. I had to pause the video to look through a few things, and I'm not too sure why it's load balancing between those two. My thought is this is a symptom, and I'm pretty sure about this. It's probably a symptom of using the multi-point interface because look at these costs. They're exactly equal, 205, 120,000. Same thing as this, 205, 120,000, which is, these are all being learned from this point-to-point interface. My thought is since router 1 is receiving these routes from two neighbors that have exactly equal bandwidth. The router 1 is saying, okay, well, this neighbor is as good as this neighbor. I can reach them just as well through both of these. Regardless of the metric I'm receiving, they're both equal cost because the bandwidth is the same on the multi-point interface, so it's going to end up load balancing between those two. So that'll work. Well, we should be able to ping it. Ping 170. Well, actually, let's do a trace. Trace 170.100.50.1. That should verify that indeed we are load balancing .2.5.2. So we're bouncing back and forth between both of those routers, and then it's dying on the hops back. But it looks at this point like we are now redistributing OSPF fully into EIGRP. Let's now do the other direction. We're going to send EIGRP fully into OSPF on both router 2 and router 3. What do we have to gain from doing that? Absolutely nothing. But that sounds like something like they would have you do on the CCIE lab. The reason I say that is because both router 2 and router 5 know completely about EIGRP routes, learning them from EIGRP themselves, since they are really autonomous system boundary routers. Well, I guess here's what we gain. Let's say router 5 loses this WAN link. If that WAN link were to go down, it would then know about all the EIGRP routes from router 2, redistributing them into here. So it would be able to use router 2 as an exit point. So yes, we do gain redundancy in this point. It's not absolutely nothing. So let me jump into the config here. Clear that off on router 5. And let's start off. I'm going to go on to router 5 and go into global configuration mode and do a router OSPF 1, because now we're redistributing EIGRP into that. And the verification for this is pretty much going to be that we don't have a loop. We're not going to end up with router 1 getting all these routes back, and we shouldn't have a loop because of that match filter we put in place on the EIGRP redistribution. So I should be able to fully redistribute EIGRP into OSPF. I'll type in redistribute EIGRP 500, and we'll do subnets. That's one of the keywords for OSPF, and we'll get more into this when we hit the OSPF nugget specifically. We'll say redistribute EIGRP 500 subnets. They're going to come in, and we need to set a metric because I don't have any default metric. And I will say that these routes will come in with a metric of 500,000. Let me just double check. That should be it. So we're now redistributing them fully on router 5. Let's jump up to router 2. Do the same thing. Router OSPF 1. Redistribute EIGRP 500 subnets. Metric. I'll even set a higher one on here just for a little double protection. Metric 600,000. Metric really doesn't matter in this case because if something fails, these routers aren't going to care what the metric is. They're just going to say, that metric is better than nothing. So at this point, we should be doing that redistribution fully on here. When we do a show IP route, we see OSPF external type 2 routes appearing in the table coming from the other router. So these have now been advertised and replaced on router 2 coming from router 5. Holy smokes. Look at what just happened, guys. Let me take you back to the topology. Router 2 was learning about those routes. It looks like, let me go back to the figure here. All the 155.155 routes, router 2 was learning about them from router 1 directly. So what on earth? It's replaced those routes it learned directly, and it's now pointing to router 5. So it's using router 5 as an exit point out of this system. This makes me think of something as well. Let me jump over to router 5. Show IP route. And it looks like right here, it is using the external routes from EIGRP. So why on earth is that happening? I mean, why on router 2 do we have these routes? Why did it replace them with the OSPF external routes? Well, that's the pop quiz of the day for you. Here's why. Administrative distance has everything to do with this. The administrative distance for an external EIGRP route, 170. I feel like an American Express commercial here. External IP routes, 170. OSPF routes, external or internal, 110. Those ending up in the routing table, priceless, because router 2 is now getting routes from external EIGRP, that's external EIGRP receiving them right here, but now it's also receiving OSPF routes right here. So what it's saying is saying, well, administrative distance-wise, these are preferred to the external EIGRP routes. And if these were the same bandwidth, we just caused some inefficient routing, because now router 2 won't be using the WAN link that it has directly to router 1 for any of these routes, any of these loopback interfaces sitting over here in the RIP domain. It's going to go through router 5 to get out to those routes. So how do we fix it? Well, what we would have to do is go under the EIGRP routing process and set the administrative distance lower on the EIGRP routes than the 110 of OSPF. So router 2 will get those and receive those directly and prefer those. And that's just using the administrative distance. We actually did that in the RIP nugget if you want to check that out to reset the metric. But as we begin to wrap up and wind down this configuration example and wrap up the EIGRP nugget, there's one more command I do want to make sure you know about, and that is the ability to do summarization. As of right now, we have not done any summarization. Matter of fact, we turned off auto summarization on all our routers to keep it from happening. But if you want to do summarization, many of you probably know the command, but I just want to review it with you. Let's say on router 1, as I can receive the 155 routes coming up from here. Router 1 is going to receive those on its serial 0.2 point-to-point interface. And let's say on the way out, I wanted to summarize to all of the router 3, router 2, and router 5. I want to summarize all the 155 routes with, we'll just do a 16-bit mask. The way I would do that on router 1 is to get into interface serial 0/0.1, and I'll do an IP summary address command. Once we're doing a summary address, we choose the EIGRP routing protocol for 500 as the autonomous system, and we'll say the summary address is 155.155.0.0 with a subnet mask of a 16-bit mask. You can set the administrative distance on this if you'd like to as well, but we'll just say enter for now. And that will reset that and resend that information to those neighbors. The beauty of EIGRP, this is one of the major advantages that it has over OSPF, is the ability to summarize anywhere. I can summarize under any interface in my network. I could summarize these OSPF networks when I was sending them over to the RIP domain, wherever and whenever I want to. It's able. Now with OSPF, you only have those specific routers, the Autonomous System Boundary Router and the Area Border Router that can do summarization. And let's verify that this is happening. Okay, there's no, it just starts sending it out and it'll replace the other routes with it. Let's hop on down to router 3 down here. We haven't been there yet. Do a show IP route. Nope. Has it, we haven't been here yet for good reason. Let me make sure it's still running. Do show IP protocols, and I know we just reset it, so let's see if the routes are going to show up. Show IP EIGRP neighbors. It hasn't formed a neighbor relationship yet, and I did reset that process, so I'm going to pause the video and give it just a second. That always seems to happen. As soon as I pause the recording, the neighbor relationship shows up. Let me do a show IP EIGRP neighbors again. There, sure enough, our neighbor has appeared. And before I even do a show IP route to verify the summary address, let me just go over this command, because this is a really good troubleshooting if you're not getting any routes. Really good command to use. When you do this command, the first thing you see is an H. This is a very undocumented part of this output. It's hard to find anything on Cisco's website. This stands for handle. It does not stand for hop count. That's what a lot of people think. The handle is just a random number that the EIGRP routing process assigns to each neighbor. It really is the order that the neighbors were learned in. Matter of fact, let me jump up to router 1 and do a show IP EIGRP neighbors. And you can see it's just kind of random, 0, 1, 2, 3. That's just the order that the neighbors happen to pop in to the neighbor table. Back down on router 3, you have the address. This is just the address that it's using to communicate with that neighbor. That's the address it's talking to on router 1. Interface is the interface it's using to get out to that neighbor. The hold is the hold down timer. That's how long it will wait without hearing a hello message before it drops the neighbor. The uptime, how long the neighbor's been up. SRTT, source round trip timer. That's how long it takes a packet to get to the neighbor and back out. This is really good because it helps it time its acknowledgments and its hello packets and things like that. For example, if a router sends an update about a route, EIGRP will naturally acknowledge it. However, if it's on a slow connection, you may, if it didn't have this, it would end up saying, oh, well, wait a sec, I need to send it again. I didn't get an acknowledgement. But the SRTT helps it say, oh, well, this is a slow connection because in previous packets I've sent, it's taken this much time to get around and back to me. So this helps it time its acknowledgements. And RTO is kind of similar. It stands for retransmission timeout. This is the amount of time, and this is in milliseconds, not seconds. Amount of time in milliseconds that the EIGRP neighbor will wait before retransmitting a packet from your retransmission queue. So this pretty much holds a packet in queue to retransmit at this amount of time before it actually sends it. The queue is how many packets are currently waiting to be sent. If this goes above 0 very often, you typically have a problem because you have a bottleneck. Your WAN link is too slow because EIGRP can't even get its update packets and its packets out to be sent to a neighbor. The sequence number right here is just used to keep these routing tables in sync to see who has the latest and greatest information. So very cool command, a lot of good information that you can catch from it. All the show neighbor commands are very good for all of the routing protocols. Now let's do a show IP route. And sure enough, down here we see from EIGRP that summary route. We've summed up all of those external routes as 155.155. And look what happened here as well. Notice something's missing there. It's no longer looked at as an external route because router 1 has taken responsibility for that. We did the summary address up here on router 1 and it's saying, okay, I have those routes. If we were to look at router 1, it would still see those routes as external routes, but now all of the other routers that it's sending this summary address to, they think it's internal because router 1 essentially has claimed responsibility for them. So it looks like in this case we've got just about everything ticking on this, and we even implemented some route summarization on our topology. So in this nugget, what we did was take a look at EIGRP through the eyes of a configuration example. We started off with just the facts, some of the not so well-known facts about EIGRP, that stuff that you won't learn in the CCNP track and just by taking the CCNP certification exam that are really handy to know. The second thing that we did was get into the configuration example, which led us to the commands, all of the commands that makes EIGRP tick. We did some pretty advanced redistribution to keep loops from happening and to bring multiple routing protocols into that topology, also implementing a lot of route summarization, a lot of good practices in filtering to make sure that loops do not happen in that EIGRP world. I hope this nugget has been informative for you, and I'd like to thank you for viewing.